All right, we are halfway there for this morning. So next, we're going to talk about calculus and optimization. So when we create models in machine learning, we often need to refine them or train them to determine what parameters to use for the model. So calculus is how we approach this problem. And so to review, the derivative of a function is the slope of the tangent line to the function. So let's look at this visually. So we have a function here, y equals x squared, so this blue parabola. And we're looking at the secant lines, which are like any lines that intersect at 2 points. And we're considering what happens when we take those 2 points and put them really close to each other. So this dotted line is the tangent line to the function y equals x squared at this point, -1. And so an important property, well, first, there's all these rules that we know how to take derivatives for specific types of functions like polynomials, e to the x, trigonometric functions, product, quotient, chain rule. So all these different rules to take derivatives exactly. And so the important fact is that the derivative kind of tells you which direction to go if you want the function to increase or decrease. So in machine learning, we'll talk about having a loss that we're trying to optimize. So we're trying to go downhill, go to the minimum possible value of the loss. So calculus is the way to do this. So if we do some plotting. So what I've plotted here is the function sine of x in the blue, and its derivative, cosine of x. And you can see wherever cosine of x, the derivative, goes to 0, that is where sine of x attains an extreme value. So either a minimum, maximum, or in some cases a saddle point. Just anywhere that the function goes flat. And we'll want to go to this function where the tangent line is flat because that's the minimum of f of x. Okay. And so this process is called gradient descent. So the derivative is also known as the gradient. And again, this idea of going downhill, going toward lower values of the function. So just a little bit of Python code here. Our initial guess for where the minimum of sine of x is let's say it's at x equals 3. And then we're going to roll down the hill from x equals 3. And the learning rate kind of controls how quickly we roll down that hill. So here I've used 0.01. So in this loop, what I'm doing is, for 1,000 times, I'm computing the derivative, which is, again, just the cosine of the current value of x. I'm scaling it by the learning rate, and that's going to tell us the direction of maximal increase. So instead, we want to go in the direction of maximal decrease, which is the opposite direction. So we're changing our value of x at each step by minus dx. And so if you plot that, what you see is this nice curve where this was the value of sine of x, and then this was how many training steps we've taken. So how many times have we moved in the direction of maximal decrease? And you actually know analytically that the minimum of sine of x occurs at 3 pi over 2. And you can see our final trained value of x is really, really close to that, the value that we expect. Okay, so that's one variable. It was kind of simple in the sense that there were only two directions we could have moved, right? X in the positive direction or x in the negative direction. But that's basically enough to extend to several variables. So if we're trying to instead optimize a function of a lot of different variables, then the derivative becomes a partial derivative, where the symbol just means we're taking the derivative of this function with respect to y, and we're keeping x and z constant. So let's take the derivatives term by term. This is all constant sine of x with respect to y. Sorry. So you get 0. The derivative of y squared with respect to y is 2y, and then the z term is 0, so you just get 2y. And now, instead of just having the derivative, we have the true gradient, which is the derivative in each of the directions. So it's usually represented by this upside down triangle. It's called nabla, or this partial sub I. So that the gradient of this function, we get cosine of x, right? So derivative of sine x with respect to x, 2y, and then 1 over z. So this is the gradient of this function with respect to the coordinates. So this is really why we discussed linear algebra first. Single variable calculus looks at equations of lines, right? Remember y equals mx plus b. And multivariable calculus looks at planes or hyperplanes, just higher dimensional analogs of lines. So to visualize in several variables what gradient descent looks like, our function, in this case, it's just in 2 dimensions, x and y, and the height is just the value of the function. So we're trying to minimize this function with respect to x and y. So we go down basically the hill that's defined by the function. Right, so we want to reach these dark blue areas from some initial starting point. So this is just code to do exactly the same thing, but in several variables. So we start with an array. So let's start with, I picked this point, 0, 0, 10. And we're going to minimize this function, sine x y squared plus log z. So again, we have a learning rate, which governs how quickly we roll down that hill. And so again, for I in range 1,000, we're going to iterate over and over again. So let's compute the gradient first. So this part is the gradient, and this is just scaling the gradient. So let's look at the gradient. Since I've defined the initial x as this array of values, where this is x, the x value, the y value, and the z value, we'll have to access those elements to compute the gradient. So remember that the derivative, or the first element of the gradient was just cosine of x, or cosine of the first coordinate. So in this case, we're taking cosine of x 0, because we're starting from 0. And the second component was 2y, so that's 2 times x1. And then the third component of the gradient is 1 over z, so 1 over x2. So this is our gradient. We scale it by the learning rate. And remember, you need a minus sign to go toward lower values of the function. And this is the training curve. So we start at whatever value the function had at 0, 0, 10, and we roll down the hill for some number of training steps. And you might notice that unlike before, this curve doesn't seem to flatten out as well. And that's actually because this log of x term is unbounded. It can go to minus infinity. And so that's the first case for what's called gradient explosion in machine learning, where the gradients we're taking eventually become unbounded, or the value of the function becomes unbounded. Okay, so far I've computed these derivatives by hand, right? I've taken the function and explicitly stated this is the derivative of that function. So fortunately, this is, you don't have to do this by hand for machine learning models, which might have hundreds of thousands to millions of these variables that you're taking the gradient. So this process is called automatic differentiation. And you have to write the code in a very specific style to have this ability. Instead of symbolic differentiation, which is when you have a human or the computer doing it by hand, writing out all of these terms, you write the code in a way such that the code gets transformed from the function into the derivative. Here we're working with math on the bottom edge. On the top edge, we're working with code. So if you wanted to symbolically differentiate a really complicated function, so you might have a function with that you're composing, so like f of g of h of, so you're transforming x in a lot of different ways before computing the gradient. You would get massive expressions like this because of the chain rule. Symbolic differentiation works like this. Numerical differentiation is a variation where we're looking at these tangent lines and trying to approximate the tangent lines with this secant. So that's numerical differentiation. When you have lots of layered functions, numerical differentiation is not efficient and it can lose a lot of accuracy. Automatic differentiation is for every single function that you perform on your input variables, you're going to store some extra information. And that extra information allows you not to take the symbolic differentiation or the numerical differentiation. It backpropagates gradients from your loss function all the way to your inputs. So that's a lot of talk. That's a lot of words for what automatic differentiation is. For practical purposes, what you need to do is the following. So again, we'll start with an array 0, 0, 10. So that's our initial value where we're situated at. You do need to use a framework like PyTorch or TensorFlow. So these are kind of fancier versions of NumPy, which are designed to give you this automatic differentiation ability. So here's our function. I've defined our function in terms of PyTorch operations and simple additions, multiplications, that sort of thing. So this is the same thing as we saw before, the sine of x plus y squared plus the log of z. Instead of manually writing the code for the gradient, what we have here is when we compute the loss, or this function, we call this method dot backward. And this is where all the automatic differentiation happens. And what happens is A gets that extra bit of information. So A.data is just this 0, 0, 10 here. But A.grad is the gradient. So after we've called backward, the gradient is backpropagated from loss to A and stored as A.grad. so another field of A. So that means we just need to scale the gradient here by the learning rate. Again, go in the opposite direction to minimize the function. And you actually have to manually set this to 0. Otherwise, most of the time, it will just add the gradient of the next call when you perform this backward. OK, so you get basically the exact same curve as before. But notice here, we didn't have to write out like the derivative of sine and y squared and log, right? We just called this backward. OK. So there's a trick you can do to make some of these operations faster. You can take this decorator, it's called, and just put this right before the function that you're trying to make fast, and it will automatically speed it up. So that's basically what this is. But the important thing now is to try to understand what array shapes are. So how can we perform all of these mathematical operations on arrays? PyTorch calls them tensors, so does TensorFlow, but they're really just NumPy arrays with some extra functionality. So there's this function in Torch which creates a random matrix with values sampled from 0 to 1 uniformly. So you provide it with a shape. So these 3 numbers are the shape, 1, 2, 3. And it gives you an array or a tensor that's that shape. So you can see this is a list of lists of lists. So there's 2 nestings of lists. And just like matrices, you have to make sure that each of these lists is the same length. Each of these lists of lists is the same length, and all the way up. So you can see here, I've printed 1, 2, 3 as the shape. You can also access that by writing x.shape, which gives you this size, 1, 2, 3. Okay, to check your understanding of this, if we increase the first dimension by 1, what does that do? It gives you another list of lists. So instead of just having 6 elements here, we have 12, right? And the reason for this is so that we can index into all of these dimensions. So x0, 0, 0. That is just this entry. You can use a colon to specify, OK, I want the 0th index of the first dimension, 0 of the second dimension, and all of the third dimension. So you can see this list is actually just this first row here. And you can if you index differently, right, you see I've indexed the 0th index of the first dimension and the third dimension. And we're saying, let's get the first 2 dimensions of the second dimension. So that returns this number and this number. OK, so we've looked at shape. There's number of elements as well. And you can see we can use this operator, this multiplication sign. And this is element-wise multiplication. It's not matrix multiplication. OK. And now there's a lot of rules about what tensors you can add together. And this is called array broadcasting. So the first thing you can do is add a constant to all of the entries of the array. So it broadcasts this number into the entire array. So basically, behind the scenes, it takes this number and makes a similar tensor as the other argument, and it adds 4 to all the entries. There's also this none keyword. I think we used it earlier. And this adds a dimension with length 1, wherever you put it. So here are some examples. So we have this array, and it has one non-empty dimension with size 3. So print x.shape. You can see that the size is 3. If we index this way, this is saying, let's keep all of the indices in the first dimension, and let's append a dimension on the end. So instead of a size 3 tensor, we're going to have a size 3 by 1. And effectively, what that does to this tensor is it transposes it, adds this outer dimension to it. So this is how I would turn this array into a column vector. So actually, all of these rules apply for NumPy as well. You can index into NumPy arrays with this type of notation. OK, so that's what happens when you put none at the end. What if we index it as the first dimension? Well, instead of a column tensor, we'll get a row. So you see the shape is 1 by 3, because the 1 corresponds to where the none is in both of these cases. OK. And you can imagine doing this more and more. You can add multiple nones, and it just appends extra dimensions here. All right. The triple dots, or ellipsis, it was specifically added into Python to support NumPy and PyTorch and all these frameworks. And this just means whatever dimensions you haven't indexed, just put them in here. So what this is saying is, let's take the 0th index of the first dimension, and then all of the remaining dimensions. And there's kind of a lot of different ways to index or accomplish the same transformations of shapes. You can use this transpose function, and you specify 2 of the dimensions to swap. Or you can specify the permutation of all of the dimensions here to swap. A lot of this is it's important when you're making the models to ensure that your shapes all line up. And most of the time, you don't need these complicated indexing. And this kind of syntax, this way of writing these indices, extends to other array operations you can perform. So this is called the Einstein summation convention. And what it does is it takes all of the repeated indices that you've specified here, and it performs a sum on those dimensions. So this would be the definition for matrix multiplication. But in this case, our matrices correspond to the last 2 dimensions of A and B, and all of the previous indices are batch indices. So you can do multiple matrix multiplications at the same time. Okay. Okay, but all of this is really complicated, and you have to have a lot of practice with real data to see why this is important. So we're going to move on to an introduction to neural networks. There's also going to be a homework, kind of, that we're actually going to go through tomorrow. And this is this fourth notebook that I made. So our task ultimately will be to predict abalone age from physical measurements. Okay. So let's move on to this third session, an introduction to neural networks. Do we need 5 minutes? Let's take 5 minutes.